Hey everyone. Today I'm going to be diving deep into linked list. So, a lot of software engineers or people in the industry have heard of a linked list. Probably if you're on LinkedIn, there's a famous interview question called reverse a linked list where you pretty much have to reverse a linked list, and a lot of people have failed to land their $400,000 FAANG interview just because they couldn't reverse a linked list. And it's led the internet and a lot of people on LinkedIn to start, or probably even Twitter, to start thinking that linked lists are useless and are dumb. But I'm sorry to say that linked lists are actually used in the real world and actually solve some really important problems. So, yeah, let's just dive deep into what a linked list is. And I've been talking to GPT and trying to get an understanding, get a script together to explain to y'all what a linked list is. And I'll also be whiteboarding a lot in this, and probably in a separate video I'll actually design a linked list from scratch. And creating a linked list from scratch might sound easy, it might sound hard to some people, but like in general, I would say it's hard. Look at the acceptance rate of just implementing a simple linked list, 28.6%. Probably people are just not hitting all the edge cases. So I'll do that in a separate video. But let's just get into what a linked list actually is. So a linked list is a linear data structure consisting of a sequence of nodes where each node contains data and a reference pointer to the next node in the sequence. So essentially, let's just say we have nodes. Well, I have to click right on it. So we have nodes. That's what this is saying. It's a sequence of nodes where each node contains data and a reference to a pointer. So let's just say the data each contains is a number. Say 1, 2, 3. Each contains a number, and they're pretty much connected by a pointer, right? You would think like the other very close cousin to a linked list is an array. So let me just increase the font here. So an array, usually we have 1, 2, 3, 4. So you might be saying like, why don't we just use an array for everything? So that's a close cousin, and I'll explain deeper why we can't use array for just everything and why linked list is actually important here and when to use it. So unlike an array where elements are stored in contiguous memory location, linked lists are scattered throughout memory and each one points to the next. The components of a linked list, a node. Let me just take a picture of this right here so you could have it up at the same time. Very basic linked list. You have to reverse this for $400,000. Can you do it on the fly? You have a whole hour to do it. People have failed that, and I probably have in the past before, so I'm not knocking anyone. But after this interview, or after this video, that will never happen to you again. So, the node, the fundamental unit of a linked list. Each node consists of a data, like a piece of data, and also a pointer to the next node. The head is the starting point of the linked list, which points to the first node. So usually this is the head. The head. Let me just draw the head. Oh my god. This. I'll just write. This is the head. This is the tail. So just saying the tail is optional, but we have the head, we have the nodes, we have pointers between each node, and we have a tail. There's actually different types of linked list. There's the singly linked list, which I have here. But then you could also have a doubly linked list where each node kind of has a pointer to the one behind it as well. And that leads to that's like used to solve even more complicated problems. So that's like most linked lists. If I implement a linked list, usually I'm just going to implement the W linked list. No point in just using a singly linked list because W linked list offers more flexibility. It does everything a singly linked list does, but can also do like more because it has a reference to the node behind it. Let's see. So what is the benefits of a linked list over array? That's sort of where we get here. That's sort of where we get here. And the first one is dynamic size. So linked lists can grow dynamically. Arrays have fixed size, meaning you must define the number of elements at the time of allocation, while linked lists grow and shrink during runtime, allowing for more flexibility. What does that mean? A lot of Python users might be thinking right now that their array is like a linked list and it grows just dynamically. But instead, in Python, your array is actually a fixed size. But then when you get to the max limit, there's code that runs behind the scenes that turns your array into a bigger array. So for example, pretend I initialize an array in Python. Say in Python, I literally go like R equals array, right? What Python actually is going to do behind the scenes is create an array of like some random size and put no values there. Let's say it's going to create an array of size 2. So it's actually going to allocate in memory. What's happening behind the scenes is it's allocating it in memory like a certain continuous space in memory. So it's going to basically store null. When you add to the array, pretend I add 1. Like this is under the hood. Array, this right here is under the hood. Let's say that. So when I add 1, it essentially adds 1 here. When I add 2, 3, it essentially adds 2 and 3 here. When I get to 4, when I add like a 4th element here, what Python is doing under the hood is once it adds the 4, it takes your current array and it copies that into another array and then like another area of memory that's continuous and extends this to fit. So that's essentially what it's doing. So that's why we say arrays have a fixed size, meaning you must define the number of elements at the time of allocation, even though in Python you don't really define it. That's because it's hiding the internal details, all the things under the hood. But really under the hood, you are defining a fixed size, but Python just handles like growing that size and allocating new memory when needed when you reach the certain size, like when like that array hits its certain size. But yeah, that was a bit of a tangent of how arrays work under the hood, or dynamic arrays especially. So pretty much arrays are just like fixed size, but linked lists, these aren't a fixed size. You don't need to allocate memory, continuous memory. So pretty much it could just grow as much as it needs to. And you never need to like define the fixed size up front. You just need to like define the data structure and then just keep adding to it. And yeah, you don't have to define the fixed size. I'm kind of harping on that point because that's really one of the most important parts is like the dynamic size. But also another important part is there's efficient insertions and deletions when it comes to linked lists. So if I delete like a certain part of a linked list, it's very efficient because if I delete this, to delete that element 2, I pretty much just have to take the pointer and point it to 3, right? I'm dropping a video on big O time complexity, but that leads to a constant time of time complexity because all I have to do is take the node and point it here, right? But pretend I want to do that in an array. Pretend I wanted to remove the element 2. Once I remove the element 2, I have to shift over all of my other elements back left, so we end up with an array 1, 3, 4. Because essentially we want 1, 3, 4 in this order in the array. Right? So if I delete 2, I have to shift over everything. Pretend that array was really large. Pretend like this array was like larger than this. We have like 5, 6, ... like 1m, right? If I delete number 2, I literally have to shift 1 million elements over, and that's very inefficient. So deletions and insertions in the middle of an array are actually very inefficient, and they're O of n time complexity versus like pretend we have a big list that we have a big linked list of 1 million nodes. If I need to delete number 2, no matter what, I just have to point the first pointer to the third pointer, and I don't even care about all of the nodes at the end. So that's why that is so efficient and why linked lists are important for efficiency. And yeah, that's kind of like two of the main things. Memory usage. Arrays require a large contiguous block of memory, which can be an issue if your system memory is fragmented. Linked lists do not require contiguous memory. That's more of like more like internal details that you probably don't need to bring up in an interview. And I think we talked about this before. It's resizing arrays. It's essentially we avoid resizing arrays when we use linked lists. So we don't have to like create copies of an array and then like add more elements with a new fixed size, because that's what the array in Python is doing under the hood. So you might be thinking that why don't we just use a linked list for everything? And let me just delete some of this runtime. But the reason for that is, let me delete all this. Cool. So the reason we don't just use linked lists for everything is because of access time. Access time in an array is very fast. Accessing an element in the array is O of 1 time. You pretty much just access like array, like you just have to, if you're writing Python code, you just do like array 2. If I want to get this element, I just say array 1. If I want to get the second element, I just say array 1, and it just fetches me that element, right? That's called random access. And the reason it's able to do that is because under the hood in memory, it's storing all of the data in like a contiguous location that allows it to just like skip to exactly where it needs to. But since that doesn't happen for a linked list, we have to we can't do this random access, and actually accessing an element in a linked list is O of n time. For example, if I want to get the third element right here, I need to start at the head and I need to traverse the head and look and basically look for that third index. So that makes it a bit inefficient. So that's kind of the trade-off with it, is the random access. So I think right here, we'll summarize the pros and cons of these two data structures, and we can end the video after that. So like I mentioned, the access time between the two is different. So for arrays, you have O of 1 random access, whereas linked list O of n sequential access. And then for arrays, inserting and deleting is O of n, like I showed before, whereas for linked lists, it's O of 1. So you kind of trade off access time versus inserts and deletions, and depending on the algorithm or the problem you're trying to solve, that trade-off makes sense. And yeah, I think all the other stuff is kind of for the nerds, but I don't want to get too deep into it. I think let's just focus specifically on what linked lists are and how they relate to arrays and why they're different and when to use one or another. And that's kind of what I did in this video. So thank y'all for watching. See y'all in the next video.